In this lesson, we're going to talk about taking a quadratic function that's not written in vertex form and putting it into vertex form. So you'll notice that I started us out with, on the right-hand side of the paper, we've got a couple of sets of the graph of the function x squared. So all of these ones, and I'm not going to label it every time, but all of these ones are the generic squaring function f of x equals x squared. So for our first example, we are going to transform the function g of x equals x squared plus 6x minus 5 into vertex form. So I'm going to remind you, and I'll probably remind you again in this lesson, the goal is to get it in the form a times x minus h squared plus k. So we're going to end up having to complete a square here. And that's going to be kind of the plan when we write functions that are not in vertex form in vertex form. Now, a here is the leading coefficient. And what you'll notice about the first two examples is that the leading coefficient is just 1 or negative 1. And that significantly simplifies the work that we have to do when we are putting a quadratic function into vertex form. In the next page, we are actually going to have a leading coefficient and we're going to need to factor it out and be very careful. Here, though, this is how I approach this kind of function. I say, let's complete the square on the first two terms. So I give myself a little space here. I still write the minus 5. So you'll notice I just rewrote the original function, but with this goofy space in the middle. And now I'm going to pick some other color. I don't know, we haven't used this pretty coral red in a while, so let's use that. So let's see if you can say it with me. What do I need to add to x squared plus 6x to complete the square? So what I hope you all remember is that we take the middle coefficient, take half of it, and square. So 6 divided by 2 is 3. And when we square it, we get 9. So we have to add 9 to x squared plus 6x plus to x squared plus 6x to make it into a perfect square. But you can't just go around adding 9. If you add 9, you've changed the value of your original expression. So to neutralize it, and you'll hear me say that word a lot, neutralize. To neutralize the effect of having added the 9, we also subtract 9. So you see you have plus 9, you have minus 9. Between the two of them, they zero out. So now let's write this in a form that actually looks like the vertex form. X squared plus 6x plus 9 is a perfect square. And then minus 5 minus 9, that's minus 14. So this is the vertex form. Now, I want you to notice, thinking about the function f of x equals x squared, what did we do here, right? So thinking about it, this is f of x shifted left 3 units. Oops. I spelled the word shifted. Funny. Shifted left 3 units and down 14 units. Okay? So if we say, looking at the function f of x equals x squared, the vertex of that function was the origin. Well, where did it end up after being shifted left 3 and down 14? The vertex of G, which I'll write here, is the point negative 3, that's the shift left, and negative 14. Notice that we didn't reflect in the x-axis. So much like in the original function f of x, the vertex is the global minimum, meaning that it is at the very bottom of the graph. The vertex of the new function is also the global minimum. So that's going to impact our domain and range. So the domain, Actually, I keep saying it, the domain is not impacted. The domain is just all real numbers, but the range is all about the vertex. Since the vertex is at the bottom of our graph, the vertex starts at -14 and then goes up to infinity. So you'll notice if you look at the top of what I had written here before we started, I asked us to find the vertex, which we just did, the domain and the range, which we've also done, but also I wanted us to look at the axis of symmetry and the intercepts. So let's talk about those. So the axis of symmetry. So remember, the axis of symmetry is the vertical line that passes through the vertex. So since our vertex is at the point -3, -14, the axis of symmetry is at the point x equals -3. And now finally the intercepts. So for the intercepts, there's two kinds. There's where it crosses the y-axis and there's where it crosses the x-axis. So the y-intercept, remember, the y-intercept is the point whose x-coordinate is 0. So you need to plug 0 in for x, and it doesn't matter whether you want to look at the original function or the function when we put it into vertex form. I personally like using the original function because when you plug 0 into that, you can see clearly that all that's left is the constant term. So one thing that you all are going to get pretty used to is that the y-intercept of a quadratic function is just going to come from the constant term in the function. If there isn't one, the y-intercept is the origin. So here the y-intercept is the point 0, -5. For the x-intercept, and remember what I'm kind of hoping that you all kind of carry with you here is that a parabola could cross the x-axis more than one time. It could cross it just once, like we see here with the function f of x equals x squared, or it could cross it not at all, right, if it's just kind of floating above the x-axis like this, or it could cross it twice, which is what's actually probably going to be most common for us. So in this instance, what we're going to be doing is we're going to be setting the function to 0 to see where the x-intercepts occur. Again, you can use the original form and just use the quadratic formula or factor, or you could also use the vertex form. And I actually prefer using the vertex form unless the original expression factors. It doesn't. X squared plus 6x minus 5 does not factor. There are not two numbers that multiply to -1 and add to 0. So we're going to use the vertex form here. So x plus 3 squared minus 14 equals 0. We're going to add 14 to both sides. Then we're going to ask, well, who would you square and end up with 14? Well, either the positive or the negative square root of 14. So x is either -3 plus or -3 minus the square root of 14. So we have two x-intercepts here. I like writing my x-intercepts as points. So we have -3 plus the square root of 14, comma 0, and -3 minus the square root of 14, comma 0. Let's move on to our next example. So now that we've got one example going, I think that the next few will come more easily. So we're doing this one in red. And for this one, we're going to try to sketch the graph. The last one, the graph wouldn't have been so easy because the vertex was all the way down at -14. So you'll notice in this case, I have a negative in front of my x squared. So when I go to work it into vertex form, the first thing I'm going to do is I'm going to factor out the negative. So now watch. Since I'm going to be completing a square, and since I only really do that on the first two terms, I'm only going to factor the negative out of the first two terms. And again, I'm going to leave a space there for completing the square. And then I'm going to write the -1. I didn't factor a negative out of it. I only factored it out of the first two. So it stays -1. Now, what do we add? Let's use orange this time. What did we add? What do we add to x squared minus 4x to make it into a perfect square? Well, we take half of -4, which is -2, and square it. So that's +4. Now we have to neutralize it. You can't just go around adding 4 to things. Anything that you do that changes the value of the function, you have to undo. So your first instinct might be, oh, we're just going to subtract 4, right? Well, be careful. Because yes, you added 4 inside of these parentheses, but the parentheses have a minus in front of them. So if you combine what you did there with the minus, you didn't actually add 4, you subtracted 4 because this minus applies to the +4 too. So to neutralize it, you're not going to subtract 4, you're going to add 4. Now, if you're sitting here thinking, oh my God, how am I ever going to know if I even did this right? A good thing to do is to check. At the end of your neutralization, if you want to call it that, make sure that you're back to where you started. You don't have to do this, and you won't probably eventually, but I'm going to go ahead and distribute the negative back through. And look what we have here. These cancel, and yes, I am left back with where I started. -x squared plus 4x minus 1. Okay, so we're actually close to done here. So this is negative quantity, x minus 2 squared, minus 1 plus 4, that's plus 3. And what I want you to notice, again, thinking transformationally, what transformations do we have starting with the generic function f of x equals x squared? We have this minus on the outside, that's a reflection in the x-axis, then we have a shift right and a vertical shift. So let's write that down. This is f of x reflected in the x-axis, shifted right 2 units, and up 3. Okay, so let's actually go ahead and graph it. So again, starting with the function f of x equals x squared, the vertex is the origin. Let's see where that ends up. So first, shift right 2, so that gets you there. Then reflect in the x-axis. Nothing happens when you reflect it in the x-axis because it's on the x-axis. So then we shift up 3 and we end up there. So let's mark that. So the vertex ends up at the point 2, 3. Now the point 1, 1. So 1, 1, shift right 2, 1, 2. Reflect in the x-axis, so now that goes there. And then shift up 3, so that lands us here. So that point, which is 3, 2, is where the point 1, 1 ended up at. Let's do one more point. So negative 1, 1, shift right 2, reflect in the x-axis, shift up 3. So that ends up there. So that is the point 1, 2. So this graph looks like this. And again, I'm not going to be super careful. I just want the basic shape of it to be right. But I encourage you to work to make your parabolas look as nice as possible. I want you to notice a few things. So first of all, we appear to have 2 x-intercepts. Our vertex is a global maximum. And that, of course, is going to impact our domain and range. So our vertex is the point 2, 3. It's a global max. We could have written that the previous one, it was a global min. But since it hadn't changed from the original function, we didn't say that. Then the domain is all real numbers. And the range this time goes up to the vertex. So from negative infinity up to 3. The axis of symmetry is the vertical line that passes through the vertex. So that's the line x equals 2. And finally, for the intercepts. So the y-intercept, again, remember, I like to just look at my original function before I put it into vertex form, because all we need to look at is look at the constant term. So you see there it is, -1. So the y-intercept is just the point 0, -1. For the x-intercepts, again, I like to look at the vertex form for this. Again, I'm expecting 2 of them. So I have negative x minus 2 quantity squared plus 3 equals 0. So I'm going to subtract 3 from both sides. Then I have this negative on the left, so to get rid of it, I'll divide both sides by -1. So x minus 2 squared is 3. And then lastly, I'm going to ask whose square is 3? Well, that's either the positive or the negative square root of 3. So this is equal to 0 when x is either 2 plus or 2 minus the square root of 3. So again, I like to write my x-intercepts as points. So we have 2 plus the square root of 3, comma 0, and 2 minus the square root of 3, comma 0. Looking at the graph, remember the square root of 3 is a number very close to 2. So 2 plus the square root of 3 should be pretty close to 4. And even on our not very, very careful graph, you can see that one of the x-intercepts occurs around 4. And again, 2 minus the square root of 3, since the square root of 3 is a number quite close to 2, 2 minus the square root of 3 should be a very small but still positive number. And you see here that the other place where the graph crosses the x-axis, the x-coordinate is a small number, but it's still positive. So here are 2 examples where we take a quadratic function, granted without a leading coefficient really, and we put it into vertex form, which we then use to determine the vertex, the domain and the range, the axis of symmetry, and the intercepts. In the next lesson, we'll look at a very similar setup, but this time looking at functions that do have leading coefficients and how that impacts the process. Stay tuned. Bye.